So, good morning and welcome back. Today we'll start a new chapter, namely topological manifolds and bundles. And very likely this will be, at least in parts, new territory for you, because what we did so far was to revisit material that you very likely saw already in one form or the other, but I assume the latest, starting with bundles, there will be some new results and some new type of thinking associated with this. Topological manifolds are still topological spaces, but they're very special topological spaces. And in fact, they're so special that nobody would use simply the same term topological space for them, but they deserve an extra term, and that's topological manifolds. And all the later manifolds we're going to construct, differentiable manifolds and so on, they will all still be topological manifolds. And bundles will be a way to think about topological manifolds that have a certain structure and that underlies much of modern physics. For instance, the standard model of particle physics, in particular non-abelian gauge theories and so on. In principle, you understand, or well, really you understand their structure only if you understand the structure of bundles, and introducing the language of bundles is very useful for that. But we first start with topological manifolds, and very roughly speaking, a topological manifold is a topological space that locally looks like some RD. So roughly, topological manifold is a topological space that locally, and that's the key word here, that locally looks like some r to the d for a fixed number d. And so it's easy to draw some. So the surface of this torus, the surface of it, that's a topological manifold, T2. And we had the sphere. So again, the surface of the sphere, S2, that's a topological manifold, looks locally like R2, both of them. This guy is a topological manifold, again for d equals 2. So obviously, it's particularly easy to draw examples for d equals 2. So T2, S2. So this is the bretzel, and so on, and of course also for higher d. But so what precisely is a topological manifold? So precisely, we have the following definition. A paracompact Hausdorff topological space, MO. So you see we raise paracompact and Hausdorff to conditions here, is called a d-dimensional topological manifold and usually we do not say topological manifold, we just say manifold, but it's used here as a qualifier to distinguish it from manifolds that have even more structure, which we're going to look at later. It's called the d-dimensional topological manifold if for every point P in the set M, there exists a neighborhood. There exists an open neighborhood. That means there exists a U that contains the point, and the U is an open set of the topological space. If for every point or around every point there exists an open neighborhood and a homeo with its full name a homeomorphism, let's call it X, that takes you from this open neighborhood U into some subset of RD, so into the image, into the image X of U, which is a subset of some RD. And that must be, you see, for every point X, for every point P, this must be the same D. It must be a subset of the same R to the D, and the homeomorphism X from U into X U RD, where if we talk about a homeomorphism, we need to know the topology on this space and topology on that space in particular. Well, RD we equip with the standard topology and X of U with the induced topology. That's fine. And the U is already an open set in MO, so the induced topology will yield what you need here. So that's the definition, and that's this locality. So intuitively speaking, if you look at these pictures I drew, then in there, you've got to ask yourself, is for every point of this space, is it true that around every P there exists an open set U that contains P? Well, without the boundary, if you think in standard topology terms, such that this set U and is mapped by some homeomorphism into some subset of RD, into some subset of RD. Okay, and obviously, so you look at this space and you say, sure, locally, if you just look very closely, this looks like a piece of RD from the topological point of view. It can be deformed such that it looks like a piece of RD. Okay, so that's the definition. Well, examples. I already drew some. Maybe it's worth mentioning or worth emphasizing that looking at the whole thing through topological glasses, so looking through topological glasses, if you wish. What does that mean? Well, it means to identify all the homeomorphic manifolds, that is, identify all homeomorphic manifolds. We see that, for instance, S2, which is homeomorphic to the set, if I think that this is embedded in R2 and it inherits the topology from R2, the standard topology, but that's topologically the same as if you drew a square, so it doesn't know shape, right? Because the square can be continuously deformed into the circle and so on. So you could even, if you embed in R3, you don't need to embed, but you could embed, and you look at this guy here, where this doesn't mean that the curve ends, but it's supposed to have some 3D thing that this line runs behind this line from the point from where you look and so on. So all these guys here are actually this as a topological manifold are this S2, and the real line, if you wish, is topologically equivalent. So that's the whole line, but that's the same topologically as this guy, and that's the same as, and so on. So topological manifolds, you see, it's very easy to draw examples. For topological spaces, it was very difficult to get an intuition about their weirdness, because that's a very, very general notion. So topological manifolds are very special topological spaces, but still they cover a wide range of cases that we want to look at in physics. I also draw attention again to this word look locally like RD, which formally is encoded here in only having to have an open neighborhood around each point that maps into some region of RD. You see, this S2 is very different, for instance, from this real line. Locally, it looks like a part of the real line. This locally looks like a part of the real line, but globally, as we say, in contrast to locally, globally, this is a different manifold. For instance, this one, S2, is compact. Well, I should always say S2 as this set with the induced topology from R2 and so on, understood as this is compact, while the real line is non-compact. Okay, because compactness is a topological property. You see two topological spaces. They differ on one of the topological properties that are known to you or that you construct, maybe in certain cases, and you know they can't be homeomorphic. So there is no doubt that the homeo sign here isn't there. Okay, so those were examples. Now, as always, we want to construct new manifolds from old ones. Construction or construct new from old. And, well, a very simple way to do that is to take a topological manifold, so MO top manifold. If you wish, you can provide the dimension it should have, because that's part of what a manifold is. There's a notion of dimension. For generic topological spaces, there is no notion of dimension, but for topological manifolds there is. So if you have a topological manifold and you have N, a subset of M, then the question arises, we call N with the induced topology on it a submanifold of MO if it is a manifold in its own right. So you just have a new topological space by looking at the induced topology on the subset, and you check, is it still true that this is a topological manifold? So example, be very simple. You have R2, so M is R2 with the standard topology, always the standard topology. Look at N being all pairs xy with x squared plus y squared equals 1. So we also use some addition on R2. Look at this set. We all know that's the circle, and you can check, well, N equipped with the induced topology on N. This again is a topological manifold. It has a lower dimension than the bigger one, but it's again a topological manifold. You could also look at examples where you take the half space that would also again give you a topological manifold. A counterexample would be take again R2 with the standard topology and now take this subset, circle and another circle, and they touch in one point. That's not a submanifold of R2. It looks like a one-dimensional manifold, and in fact, around every point, it locally looks like R1, a piece of R1. But at this point here, where they touch, it looks like two R1s with one common point. So what's the dimension at this point? We don't know. It doesn't locally look like that. So this is not a submanifold. Neither is the light cone in physics, in relativistic physics. The surface here is not a submanifold of R3 in this case, because at this point here, it fails to be a manifold. And as you saw in the last problem sheet, there's a notion of variety from algebraic geometry. For instance, this light cone is an algebraic variety, but it's not a submanifold of R3 in this case. Of course, that also works in higher dimensions. So that's a very simple case. A slightly more interesting case is that of a product manifold. Definition: let MO, MOM, and NON be manifolds, topological manifolds, then M cross N equipped with the product topology M cross N is a topological manifold of dimension dim M plus dim N. So you just take the product of the manifolds and you get a new topological manifold, and this is called the product manifold. Okay, and by dim M, dim N, I obviously mean the respective D from the definition. The product manifold. For instance, example, T2 is the product of two circles. We saw this before, but we only looked at it as the product of two topological spaces. Now, these two topological spaces, well, S1, happens to be a topological manifold of dimension 1. So you take the product, you get a new topological space, which you're guaranteed, if equipped with the product topology, is then a topological manifold of dimension 2. So you don't need to check every time that something, even if it's pretty obvious. I mean, you look at T2 and you say, yeah, it is a topological manifold. But if I had asked you to look at Tn, the N torus, it's not so easy to imagine, but you just need to know the definition. The N torus is just N copies of the circle put together in a Cartesian product, and so that immediately gives you an N-dimensional topological manifold. You have other examples like a cylinder. A cylinder is S1 cross R, now taken as manifolds. You see, you always have to think at what level you are. Taken as manifolds gives you the cylinder. The cylinder is two-dimensional. But you could go to higher cylinders if you wish. Well, you get the message. So that's product manifolds. And obviously, by product taking, you can build interesting manifolds out of old ones you already have. Now, products are a nice thing. And very often in physics, we really think of one manifold as, say, the base space, and we think that at every point, and that's one way to think about the Cartesian product, you have one base space, and at every point you attach the same copy of another given space. Now, it turns out that taking the product is a good thing, but it's somewhat too restrictive. It's a little too special. And for instance, we have a counterexample. And that would be the Möbius strip. The Möbius strip, so now that's tricky to draw. Let me do something that's fail-safe here. Take a rectangle. That's the space, and take this side and glue it to that side with this orientation. So it's like a sheet of paper, you turn it around, and then you identify this line with this line. What you get is a cylinder, right? Well, if this is infinitely long. But now, let's not have this infinitely long. and let's take this side identified with this side in this direction. What do you get? You get the torus, right? You get the two torus. You identify like this, and then you bend this around, and you get the torus. That's the torus. Well, that's not the counterexample. That's obviously an example. But the counterexample is produced. Counterexample to a product manifold is produced by identifying these two sides. So you can make the cylinder, and now you glue it together in this fashion. I'm sorry, that's already the Klein bottle. We don't identify these sides. We just identify these two sides, and what you get is something like the cylinder. Okay. But, so we do not, and I'm sorry, I was already, that's also an example. I wrote down, it's the Klein bottle, but I want to do the Möbius strip. So you go around, you don't get the cylinder, but you twist one end before you glue it together. And, oh dear, okay, how do you draw this? Intuitively, I don't know. Okay, I'm ill-prepared to draw this, but you've certainly seen this. Now you take a strip, you twist this side, and then you turn around and you glue it together. It's the Möbius strip, and that thing intuitively has only one side, because you can, from every point on there, you can go to the other side of the piece of paper you have there. But that's not a product manifold. That cannot be written as a product manifold, but this is not a product manifold. Although locally everywhere it looks like a product manifold. Okay, so, and in order to get this idea formally clarified, we introduce a new concept as a kind of a generalization of the idea of a product, and that's a bundle. So I guess up there I should have written 3.1 3.1 definition and construction of topological manifolds. And now we come to 3.2, bundles. Again and again in these lectures, we will have opportunity to speak of bundles, and every time we add new structure to the manifold, we have to revisit the bundles and see what happens to the structure from the point of view of bundles. But the basic ideas, or the basic structure, the whole idea actually, is already clear at the topological level. So definition, a bundle and let's be specific here, of topological manifolds is a triple. We have three data, and the triple is E pi m, where E is a topological manifold called the base space. The total space, I'm sorry, it's the total space. Now, the M is also a topological manifold called the base space. And the pi is an onto map, it's a surjective map from the total space into the base space. And because we're in topological manifolds, we want it to be a continuous map. And it's meaningful to talk about continuity because I have a topology here, we have a topology there. And that is a bundle, nothing more and nothing less. All right. Now, we further call, let P be a point in the base space, then pi, well, I almost wrote pi inverse, but that's just a not so good notation for the pre-image. The pre-image of the set with the element p that contains only this point under the map pi. And this surjective map is called the projection. Also in names, the projection. So the pre-image of a point P in the base space under the projection, we could call this F sub P, is the fiber at the point P. This is the fiber. Okay, well, example. A trivial example is a product manifold. So let M, comma F be topological manifolds, and then define the total space to be the product of the base space, and every time you attach the same fiber, so obviously we know if these are topological manifolds, this is a topological manifold. Fine, this is a topological manifold. I also have to define the datum pi. Pi is a map from E, that means from M cross F down into M. That's what it's supposed to be. And I need to define it. Well, it's P comma, let's call this F, element of the fiber, and you map this down just to P. It's a real projection. Now you have a Cartesian product, has two factors. This P comes from M, the F comes from F, and it maps down like this. And if you equip M cross F with the product topology, which is the understanding because nothing else was said, then this map is continuous. So pi continuous in the product topology on M cross F. Well, in M is M, so we have everything together. So this way we constructed a bundle as the product of two manifolds. So certainly the notion of bundle contains the idea to look at the product. It contains that idea. Okay. But the Möbius strip we talked about previously, if E is the Möbius strip, and I have a base space M that be the circle, and then I can construct a pi. So let me try to draw this. It's more quickly drawn than written down in formulae. So what was the Möbius strip? You identify this side with that side, but before you do that, you twist, before you glue it together. But you can think of this, well, it's an intuition, you can think of having in the middle, for instance, in the middle, anywhere, you have a circle, because if you twist and you identify, but if you were here in the middle, roughly speaking, then this point will, despite the reflection around that point, will get identified with this point. And then you can agree in this picture, say, that a point lying here will be projected to this point on S1. So if once you identify these 2 points, this dotted line becomes the circle. And you can agree to always map this point to that one, that point also to that one. So that defines your projection map pi. Everything is fine, and that's continuous and all that. And you find that the Möbius strip is not the product of S1 with the interval, but nevertheless the pre-image of any point P on S1, so that's the point P on the S1, under pi, will always be the interval -1 to 1, say. Because that's at every point you attach that same interval. Okay? But it's not a product manifold because you don't identify like this. It would be a product manifold. You start twisting it, and at some point the fibers meet like that. Okay, so Möbius strip therefore is a bundle, but not a product. Not a product manifold. Okay? And there you see our notion of bundle. I point this out again. So it's very intuitive to think of the total space as some base space such that to every point there is a fiber attached. But that's the special example. If you carefully look at the definition, you see there is no mention of the total space somehow being built from the base space with something attached to it. It's weaker. It says there's a total space and you have a projection map to the base space, but there is no previous assumption on this total space being built in some particular manner of the base space. And that is the generalization, whereas in the product case, you have this preconceived notion that you have a base space and a fiber that's being attached. Hence, the bundles are a generalization of the idea of taking a product in this subtle form, and this is wildly important. Now, sometimes if we have a bundle, we use the notation, well, maybe I first erase the blackboard. So yet another example would be afforded, for instance, by taking the real line as the base space and then attaching at every point a circle to it that looks like a cylinder, but because topologically it doesn't matter how big that circle is, you could shrink down to a point and then afterwards start attaching small intervals or something like this, and so on. Okay, so that would be the total space. And then you have a projection map pi down to the real line that's continuous. And this would also not be a product. Why is this not a product? If you look at this point Q and this point P and this point R in the base space, then you find that the pre-image of the point P with respect to pi is a circle, so that's the fiber at P by definition. You find that the same at the point Q is just the point. What space is this? Well, it's just the point, okay? That's the fiber at Q. And if you go to R, then the fiber is just an interval. Okay? And that's the fiber at R. And these are all not homeomorphic. That means in general you can have a bundle, but the fiber space needn't be the same everywhere. It simply needn't be. If it is, that's a special case definition. Let E, M, and sometimes we write it this way, pi be a bundle. It's the same data and it emphasizes that pi goes to M. Let this be a bundle for which, such that, for all P in M of the base space, the pre-image of the set P with respect to pi is the same, or if you want homeomorphic, to the same F for some F, for some manifold F. Then E P M is called a fiber bundle. Fiber bundle with typical fiber F. So it's a little less general than a bundle, but it's still much more general than a product. It's a fiber bundle. Examples. Well, I think the examples we gave before are examples. Another example is the C line bundle over some manifold M. That's just a name. Why do we call it C line? What's a line bundle? Well, line just refers to the fact that this is C to the 1. C line bundle is a fiber bundle E pi M with typical fiber C. Okay. If we have a fiber bundle, we also often write, okay, and I'll write it here, notation E M. So we put this down, it's more like projection, and then we very often draw a diagram like this that we say the fiber goes in there, but it's really the understanding that this is the fiber of this bundle. This is just, we say this is a fiber bundle, and that's usually quicker than saying let this be the total space, this the base space, this the fiber with respect to this. We just draw this picture. It's just notation. Now the C line bundle over M will play a very important role in quantum mechanics, and by way of the following construction, definition. Let E pi M be a bundle, then a map sigma that starts in the base manifold and maps into the total space. So it's not in the projective direction, it's the other direction. Such a map is called a cross-section, or a section is called a section of the bundle if, now this is part of the bundle structure, the base space, the total space. We haven't used the projection map yet. It's a section of the bundle if you can first apply the map sigma to go from M up to the total space, but then you apply the projection afterwards, and if this leads you back to the identity on the base space, then you have a section. Well, as a picture to this, we have the base space M, and let's look, this is for a general bundle, but let's consider the case of a fiber bundle to draw a picture. So at every point you attach the same topological manifold F, and then it's clear the whole picture is the total space, and if you have this point in the total space, then the projection map will take you down to this base point. Okay? If you have this point in the total bundle, you've got to see, okay, there's a fiber coming with it. The pi takes you down to this base point, and any other point on that fiber is taken down to the same base point. Now, this is the projection map. Now, what is a section? A section, as it says, is a map that takes a base point, let's say this one, and point in the base manifold M, and it maps it to some point in the total bundle. So I could take this one and map it to this point in the bundle, right? In the total space. I can do that. But if I do this, so this would be where the map sigma could take me, but then you apply the projection afterwards, and you do not end up at the same point in the manifold M. That means pi after sigma is not the identity on M. Hence, this is not a section. That's right. Clear? It's only a section, intuitively speaking, if you always map by sigma into the fiber over that point, because then pi takes you back to the base point. And the map sigma does this for every point in the manifold. Okay. Now, special case. Let's assume the bundle is in fact a fiber bundle, but even more, it's a product bundle. So let's assume that the total space is the product of M and some F, and that pi is the projection to the first factor, like we had it before. You go down to M, so that's a bundle that's constructed like this is a product bundle. And it's nothing but the Cartesian product of manifolds, right? And you see every product bundle is in particular a fiber bundle, because if you take the product, then every fiber is the same, namely the second factor you chose. Okay? You have this, and in that case, only in this case, can you understand the sigma, the cross-section? So let's take a section. Only in that case, a section sigma that takes you from the base manifold to the total space, which is now this product, can be understood as taking a point P in the base space and sending it to the pair P, and let's call this S of P, where S is a map from the base space into the typical fiber. This is just a map without further conditions. And that's our intuition. Well, if you tell me for every point of the base space the element of the fiber, then, and that telling the element of a fiber is just a certain function that you need to give me, then what's the difference between a section and a function? Because from the function I can construct the section. Yes, but you only can if the total space is a product. But bundles are more general than products, okay? So in general, for a bundle, this is a different notion, okay? So in particular, physics example, we could look at a C-line bundle over M in quantum mechanics. And a C-line bundle need not be the product of M with C, okay? It's just a fiber bundle. And in fact, a wave function, what usually is called a wave function in quantum mechanics, is not a function at all. A wave function is actually a section of the C line bundle over physical space, for instance R3. And one always pretends the wave function is a function. It's a function that goes from the physical space into the complex numbers. That's the wave function. Now, if it always were the case that the C line bundle over M is a product, M cross C, then indeed, wave function would be the appropriate term, and making this into a section would be just cumbersome, would just be unneeded formalism. But it's just not the case. It's just not the case that you can always do this, and you can get away with not doing this as long as you stay in Cartesian coordinates on the physical space. You don't know yet what coordinates are. I'm going to introduce this later. But in fact, a C line bundle is something more special than attaching a complex line over every point. Okay, so you need to think about this carefully. Maybe I should just write down this kind of sequence. So you have a product manifolds, you have fiber bundles, and you got bundles. So product manifolds are contained in all the fiber bundles, and fiber bundles are contained in all the bundles. So this is the degree of specialization. So if you had a product manifold, you could talk about a wave function if that was the structure in quantum mechanics, but in fact you have only a fiber bundle. Okay, but a product manifold, so fiber bundles are between product manifolds and bundles, but they're still much more general than product manifolds. So you should look at this at home, compare the definitions, and see that it's all very simple. It's just a lot of terminology at once. Right, and I'll come back. I mean, it's not like the physics example is not to be understood at the moment, it's just a hint to what is to come. And that these constructions are not mathematical extravagance, but that they are rather intimately connected with questions and structures we look at in physics. Now, once we have a structure like bundles, we need to understand and classify these structures. For instance, we have the definition. If E pi m is a bundle, then E prime pi prime m prime is a subbundle of the previous bundle if E prime lies in E, M prime lies in M, and if you look at the map pi, which goes from E to M, and you restrict it only to the subset E prime, then that coincides with the pi prime map. That's a restriction. So it's the subbundle. Okay. And that's one definition. And the other definition is the restriction of a bundle. So again, let E pi m be a bundle. And now consider a submanifold n of m. So you see, bundles use manifolds, and now if I say n in m, I mean submanifold. And in fact, up here I should have said the same. So these two are meant, these symbols, these subset symbols, are actually supposed to mean submanifolds. Okay, because obviously if this E prime and M prime were not submanifolds, you couldn't speak of a bundle here. Okay, so consider n and m a submanifold, then the bundle, okay, what is it? Consisting of, you want to go down to n, and you need to take the pre-image of the entire set n under the projection map pi on the original bundle, and define this projection pi here as the restriction of the original projection pi here to the pre-image of n under pi. Okay, then these data, total space, base space, projection map, is called the restricted bundle. Namely, you start with a bundle and then you only look at it over a subset of the original base space. And that's restriction to this subset in the base space, and only looking at the bundle over it. This bundle over it is this restricted bundle. Again, it's a very simple definition and very useful. Now, it's also very important to see in which cases two bundles are to be considered the same. So consider two bundles. One is called E pi m, and another bundle that's called E prime pi m prime, but there's no prior relation between this E and E prime and M and M prime. Oh, and this is the pi prime, right? Just two bundles. Then the two bundles are called, okay, two bundles, and consider maps, two maps. One is a map U that takes you from one total space to the other total space, and you have a map F that takes you from the base space of one to the base space of the other. Then these two maps, then the pair UF is called a bundle morphism, if, now let's draw this diagrammatically, it's really very simple. So you go from E to E prime by the map U, and you go from M to M prime by the map F. Assume you're given these two maps. If they're such that you look at the projection pi here and you look at the projection pi prime there, if this diagram commutes, then this pair UF that maps the total space to the total space and the base space to the base space, then this pair is called a bundle morphism. Well, maybe we should spell out once again what it means for this diagram to commute. It means you can either go this way from this E to M prime, or you can go that way, and it should give you the same result. So that is pi prime after U, pi prime after U is the same as F after pi. And you see, you need to use this projection map here, and then this is called a bundle morphism. Now, is this already structure preserving? Well, what's the structure of a bundle? Well, the structure of a bundle, you have the base space, and you have this projection map, and if you preserve the fibers, if you have two bundles whose fiber structure is the same, then these bundles are isomorphic. But formally we say, definition, two bundles, the same as before, E pi M, E prime, pi prime, M prime, are called isomorphic as bundles. If there exists a bundle, if there exist bundle morphisms UF and, how do we call this? Well, probably it's U inverse F inverse. If there exist bundle morphisms UF and U inverse F inverse. What does that mean? Well, it means that actually this map that takes you from here to there, you can go back by U inverse, and in both directions it's a bundle morphism. Okay? Then you have the pi map here, the pi prime map here, M prime. You go by F here, but there exists the inverse of F, so U and F are both bijective, but also in both directions these are morphisms. If you have that, then the fiber structure of this bundle is the same as the fiber structure of that bundle. That's easy to see. So such UF, obviously we have a UF whose inverse is also a morphism, such UF are called bundle isomorphisms. Bundle isomorphisms. And they clearly are the relevant structure preserving maps. for bundles. Remember, the recurrent theme is that you study a structure by studying its structure-preserving maps. Okay. So you could have two total spaces, E and E prime, that are homeomorphic, isomorphic as topological manifolds. And they have respective base spaces, M and M prime, that are homeomorphic as manifolds. But they're just not isomorphic as bundles, because in one, the projection is defined differently from the other. If that is the case, everything can be at lower structural level be isomorphic, have the same structure, but as soon as you take the projection map into the play, for instance, if you have the cylinder, or in comparison to the Möbius strip, the projection map will be different, because the cylinder has typical fiber interval -1 to 1, say, right? And the Möbius strip has. They're even both fiber bundles. They have the same base space, namely S1, but this twisting is encoded, of course, into how the projection map looks like. Okay? Because the projection map needs to be continuous. You cannot say, oh, I just take the projection map of the cylinder and then I twist it and I join it, because then the projection map would have to take, at the point where you join, a point up here down there, but the next point it takes there would be this one from down here, and that is not continuous. Think about this, okay? So the cylinder and the Möbius strip, if you look at them as, if you look at the total spaces, they are homeomorphic. Yeah, they must be, but as bundles, they're simply not. Okay? That's important. And hence, we need a notion of isomorphism of bundles. Aha. Now, think about this. A topological manifold was a topological space that was locally homeomorphic to some part of Rd. Now, not homeomorphic, that would be too strong. I mean, all topological spaces that are homeomorphic to Rd are, seen through topological classes, Rd. Now, you look at two bundles, we now have a notion of isomorphism of bundles, okay? But that's, again, very strong. We could weaken this as well to local isomorphism of bundles, and that's the next definition. You see, these are a lot of definitions, and that is because we're developing the language. But once, you need to trust me that you need to know all these definitions, and you should think about them, and you should memorize them. Okay, so definition, a bundle E pi M is called locally isomorphic as a bundle. I read out locally isomorphic as a bundle. Sometimes we suppress this if for every point P in M of the base space, if for every P of the base space, there exists an open set U that contains the point P. So it's called locally isomorphic to another bundle, E prime, pi prime, M prime. If for every P in M there exists a P in U and O, such that the restricted bundle so we take the original bundle and we restrict it. So how did we construct this? This was the pre-image of U with respect to pi mapped to u, and here the projection map was defined as the restriction to pre-image of pi of u. If the restricted bundle, namely to this open neighborhood of a point P, is isomorphic to the second bundle, E prime, pi prime, M prime. So these notions I'm developing here, they're developed in order to further elucidate the connection between bundles, product bundles, fiber bundles, and so on, and to some extent to quantify this relation. And there is some terminology that's heavily used, which we don't need because we already have all the definitions on the blackboard, but because it's so heavily used, I name it. So we have the case that a bundle E pi M is called trivial if it is isomorphic to a product bundle, which then necessarily is of this form, some pi that projects to the first factor M. And we said this before. I think it's still up there. Yeah, I said that's the product bundle. That's a particular product bundle, but any bundle is trivial if it's at least isomorphic as a bundle to the product bundle. So we're back to base 1, where we said, well, products of manifolds we understand, and if we wish, we can look at a product because if we, as a bundle, because every time we take a product, we can of course project back to the first part. So a product of manifolds immediately introduces a bundle. That's a very trivial case we started from and which needed generalization, as we said. Okay, so that's this. But then there's the notion of a bundle being locally trivial. So a bundle E pi M is locally trivial. And that's a different beast. It's locally trivial if it is locally isomorphic to some product bundle. Okay, that's locally isomorphic to some product bundle. So example, and obviously trivial implies locally trivial, but not the other way around. So example, the cylinder is trivial as a bundle, and hence also locally trivial. Now the Möbius strip is not trivial as a bundle in this sense, but at least it is locally trivial. Okay. Now, a locally trivial bundle is not yet a fiber bundle because it could change the fiber along, right? But it just locally, it everywhere needs to be locally trivial. Yes?
Could you give an example where something is not locally trivial? Because it always feels like you could, well, reform it in a way such that it is.
Yes, they're hard to come by. In fact, what we will do, that was the next sentence, we'll always restrict to local triviality. Yeah, it should be possible to construct something that's not locally trivial. Well, yeah, I mean, a bundle that very quickly, I think what I drew down before, I have a base space. And here I attach a Here I attach at every point a complex line. And now, from a certain point onwards, I decide to attach a real line. So here, over the base space, I attach a complex line up to here. And this line is now a real line. And from now on, I only attach real lines. Now, that means locally, this looks like a... so you go to an arbitrary point, you look in its, and you find an open neighborhood U, and you look whether restricted to this neighborhood U, you look at the restricted bundle, which is very easily thought of as not looking at the rest, and you ask, is this isomorphic to a product bundle? Yes, it is. It's locally isomorphic to M cross C. The same you can do here. You take an arbitrary point, you look at some, you need to find one open set around every point, such that locally it looks like a product bundle, yes, M cross R. But what about taking this point, any open neighborhood you take in the base manifold doesn't look like a product, because in one half it's cross C, in the other half it's cross R, or the other part. So this construction is clearly a bundle, because I can always say, well, I project this down here, and maybe I get this, can do this in a continuous manner. I think one can. And so this is not locally trivial. Okay, fine. So that's heavily used terminology, and from now on, only consider locally trivial bundles. And that has an immediate implication, and the implication is locally. So if you restrict to some part of it, locally, every section, any section of a bundle can be represented as a function or as a map from the base space to the fiber, from base space to fiber. Okay? But again, only locally, because globally it's not a product. Okay? So there will be various problems on the problem sheet to get this clear. So if in quantum mechanics you have the C line bundle over some physical space and it's still locally trivial, then on some patches of the physical space, it's perfectly fine to talk about the wave function. It just could happen that on other parts of the physical space, you go to some other patch, you need to choose another function representing the whole global section. Well, if the global section exists at all. We'll come to that. Okay. So that's the triviality and local triviality of bundles. And before the break, let me make one more definition, a very important definition. It's the so-called pullback of a bundle. Definition. Let E projection pi M be a bundle and let there be a map F given that starts in some space M prime and embeds it into the space, or sends it to the space M, to the space here. Then we can construct the so-called pullback bundle pullback bundle from these data, namely from the data, from these data as they're written there, the pullback bundle, as, well, what do I need to do? I need to give you the total space. So I already have the base space of this pullback bundle that I want to use as the base space, but now I need to construct over it the total space. I construct over it the total space, and this total space is constructed as M prime cross. Now maybe you get suspicious because you say, oh, so the pullback bundle is going to be a product bundle because I write cross. Well, but I cross it not with some fiber from here, but I cross it with the entire total space. Sorry, this is E prime, the yellow E prime. I cross it with the entire total space of the original bundle. It's huge. But then I impose a restriction. And the restriction is that if I use here the projection map pi prime, which is defined as pi prime taking an element m prime in m prime, and an E that lies in this E, I mean, it's this product, that it maps it back to M prime. The restriction is that if I use the projection map and then F, hang on a second, how is that? Is F hang on, I need to go up here. Aha. So I take so I should get F of M prime is M, is the same as pi of E. Aha, yeah, now I know why I had to hesitate so long. So I don't take, I only take, I'm sorry, I only take those M prime E out of this M prime cross E that satisfy this condition, that satisfy that I project the E down by the pi, and I obtain the same as if I had taken the M prime and mapped it by F over here. So I'm sorry, it's of course not the entire space, that's what I wanted to construct, it's a huge space, but I only take those elements that satisfy this condition. Okay? I'm sorry, so that took a second. So that's the pullback bundle here. Okay, it's the pullback bundle. And once you have that, you can, of course, also construct immediately a morphism over here from the original data. You can construct this morphism U here that takes you from the M prime E's that qualify under this condition and map it over to E. So from the white data, you can construct the yellow data, and then this left column here, E prime, pi prime, M prime, is called the pullback bundle. E prime, pi prime, M prime. That's the pullback bundle. Right. Remark. Sections on a bundle pull back to the pullback bundle. What does that mean? It's very simple. You take a bundle, E pi M. But you don't only have that bundle, you also have a section sigma, which you know has this condition that pi after sigma gives you the identity on M. That's the construction you start from. And then you got some additional data F that takes a base space M prime into M. Now, from these data, we already know that we can construct the pullback bundle here, E prime, pi prime, M prime. This is what we just did, including the U, such that U and F together are a bundle, constitute a bundle morphism. Not isomorphism, that could be, but it doesn't need to be. Now the question is, once you pull back the bundle, can you also pull back the section? That means, can you construct from the section on this bundle, can you construct a section on that bundle? And the answer is yes, you can. You can construct the green section sigma prime on this pullback bundle. And it's your homework to consider how to construct sigma prime. But if you look at this diagram and you look at the data you have, obviously what you need to do, sorry there's a prime missing here, you need to construct from the F and this sigma and this pi, you need to construct a map sigma prime from M prime to E prime such that pi prime takes you back to the identity. Pi prime after sigma prime takes you back there. It's not difficult. There's actually only one possibility how you can construct from the given data this sigma prime. And that is what one means. You see, you have a map from one base space, from one space into the base space of a bundle, and on that bundle you have a section. You can pull the section back to the pullback bundle. Okay? So the only data in addition to a bundle with a section you had was this M prime goes to M. And from that you can construct the whole picture. And that is used very heavily. So let's have a 5-minute break. Next we consider 3.4, I believe, and it's in an entirely different spirit from the bundles. The bundles are covered now, and we'll revisit bundles only later when we have more structure. Now we'll look at something that's actually fully redundant. We don't need this for topological manifolds, but pedagogically it will be invaluable later on. And so that's the topic of viewing manifolds from atlases. So definition. Let M, O be a topological manifold of dimension D. Then a pair U, which must be an element of the open sets of the manifold, a pair UX, where U is in O, and X from U to X in U, which is a subset of RD, is called a chart of the manifold. What is new in this definition? Well, absolutely nothing. It's only that these maps I defined before, which we know in a topological manifold, which is a paracompact Hausdorff space, that around every point of the manifold there is an open neighborhood U, such that there exists such an X. that this pair of the open neighborhood in the manifold together with the map that maps it into a part of RD, that this pair be called a chart. Well, so it's not a definition, it's almost only terminology. Okay? But it's extremely useful terminology, and we'll come to that. It's a chart of the manifold. The component functions of X, well, what's that? Well, X lands in RD, but what is RD? RD is a Cartesian product of lots of R's. Now, if I have such a map X, I can ask, what is the result of mapping a point P in U into RD? What's the result in the first entry? What's the result in the second entry, and so on? So the component functions of X, these are the maps, let's call them X up I, of that go from U now only to the real numbers, and is defined as taking a point P and mapping it to the ith component here. So if you want to be very formal, you can say it's the projection to the ith component of the result of the application of X. So you only look at the ith component of this. The component functions of X, Xi, U to R are then called the coordinates of the point P, which must lie in U, with respect to, and this is very important, with respect to the chart Ux. So we cannot speak of the coordinates of a point, we can only speak of the coordinates of a point with respect to a certain chart. Now, all your life in physics so far, your education in physics, has taken place in charts. In classical mechanics, you said, let's have a particle in R3 move like this, and then you were told the coordinates of that particle at various points. Or even in Lagrangian mechanics, you wrote down the x1 to xd in a d-dimensional configuration space and so on. Your life took place in charts. And that's fine, but, well, the question is, what happens if you look at the same point with respect to different charts? You could certainly have that, because if around every point of the manifold such a pair exists, like the definition of a topological manifold guarantees it does, then you certainly have overlapping charts. So let's first have a remark. Obviously, there exists a set of charts, set curly A of charts, such that if you take the union of all the U's in there, so the U, if Ux is an element of this collection, then you do the union over all the U's, and then you recover the manifold, because every point is covered by some chart. And there will be many charts that overlap, that have non-empty overlap. Okay. Then we immediately have another fully redundant definition, which in later chapters will be changed slightly. Okay. Definition: two charts. And such a collection of charts is called an atlas. A is called an atlas. And the idea is clear. If you have the whole world, and the whole world is covered with charts, you can print the charts and stack them together into an atlas. and you can turn the pages of the atlas, and you can look at, on page 300, there's Paris, and on that page it has the coordinates 2 centimeters to the right from the lower left corner of the chart, 2 centimeters up, that's Paris. Now, you turn the pages and you come to a later chart, and again Paris appears there, because now the charts are all overlapping. Paris appears there, but now it has different coordinates. So the coordinates of Paris, well, with respect to a certain chart, that makes sense to write down the coordinates, but the coordinates depend on the chart. Paris doesn't have the property to, I mean, Paris as such doesn't have the property to, in this and that type of publisher's atlas, to be at these and those coordinates. Paris is Paris. The coordinates depend on the chart. Now, you have two charts, UX and VY, let's call them like this, are called C0 compatible. And this C0 later on will be changed in C1, C2, CK, C infinity, C omega, all possible kinds of other C's. But here it's just a name. It's called C0 compatible if either A, well, you're certainly compatible with someone if you never meet that person. So if U intersected V is the empty set. So if the charts do not overlap. Or B, if U intersected V is non-empty, if the charts overlap, then we have the following situation. We have the chart U, and we have the chart V, and if we start from U, we can actually look at the coordinate map X, so the components are the coordinates, goes into RD. Well, it actually only goes in X of U that lies in RD. And you have the chart V, you go down with Y, you go to Y of V lying in RD, that's the situation. But now if the charts overlap, then in the overlap you can apply either the coordinate map X and you land in X of U intersected V, which is a part of RD, or to every point in the intersection you could also apply the chart, the map Y, which yields Y of U intersected V. And of course, you could also look at this path here, which is Y after X inverse. Okay. And so Y after X inverse goes from X U intersected V to Y U intersected V, which is a part of RD. And that's the key observation here. All of a sudden, should put this in yellow, all of a sudden you have constructed a map from RD into RD from two chart maps, and two charts are called compatible if this map Y after X inverse, which strictly speaking goes from this subset of RD to this subset of RD, if this map is continuous as a map from RD to RD. Well, it is a map from RD to RD. What I want to emphasize here is that you can now decide on continuity without knowing anything about the topology of your original manifold in which these intersections are taken. It suffices to know the topology of the charts in order to decide whether this is continuous. Now, I think we showed that. The composition, so these are homeomorphisms, so X inverse existence also continuous. The composition of two continuous maps is again continuous. Because this is continuous, path back also continuous. This is always the case. This is always the case on a topological manifold. So hence, any two charts in a topological manifold are C0 compatible. Okay? So it's at first sight fully redundant to have this definition because it applies to any two charts. However, later on, we want to establish a notion of differentiability as well. Now, the manifold still staying a topological space, we have no way of saying that these maps into the coordinates should be differentiable, because for that we would have to have a differentiable structure on the manifold. What we will do instead, we will later on require that two charts be C1 compatible, C2 compatible. So once that there shall be continuously differentiable once or twice or k times or infinitely often as maps from RD to RD. But because we understand differentiation on RD, we can do this later on. It's only for topological manifolds we introduce the notion and this idea, and later on we refine it. So as I said, fully redundant, but it's a useful notion. And again, all your life in physics took place in charts. And whenever you talked about changing coordinates, you talked about this map. Because you lived in one chart, you looked at the problem in one chart, say Cartesian coordinates, and then you went to other coordinates. So the coordinate changes in physics, in the standard physics courses or introductory physics courses, is between charts. But you never consider the real world that lies over it. Well, the real world in that sense is the manifold. And what kind of chart you choose is largely arbitrary. But whether you express some particle path, some curve in one coordinate system or the other coordinate system, that doesn't change the particle path. Right? That's just up here. That's one curve in the manifold, and this is coordinate changes. So remark, the map y after x inverse, and of course you can also invert this, then you get x after y inverse. The map y after x inverse is also called the coordinate change map. So in a sense, you only perceive physics down here on the chart level so far, unless you saw this in, say, general relativity. But actually the abstract notions, coordinate-free notions, lie above that. So that makes this connection. Definition. A C0 atlas, curly A, is an atlas, that is a collection of charts, is an atlas whose charts, whose elements, whose charts are pairwise compatible, C0 compatible. So again, remark, I said it before, obviously, any atlas is a C0 atlas. That will change later. If we impose stronger conditions on the compatibility of chart maps, of coordinate maps, not every atlas will satisfy these conditions, and that is one way to give extra structure to manifolds, in particular differentiable structure. And there's one more definition. An atlas is called maximal if any chart Ux that is C0 compatible, so I should say a C0 atlas, is called maximal. If any chart Ux that is C0 compatible with any Vy that lies already in the atlas is already contained in the atlas. So now here it is not the case that any atlas is maximal. Remark. Consider the following. Consider the manifold MO being the real line equipped with the standard topology. It's a topological space, but it's clearly locally homeomorphic to R1, so it's a one-dimensional manifold. And so for this one-dimensional manifold, I claim that taking the entire line together with the identity on R is an atlas of this manifold MO. It's an atlas. Well, that's what you usually do. You say, well, if all of physical space is R, then I can obviously use 1, 2, 3, 4, 5, pi, 7.5, and so on as coordinates on there in this fashion. So you have an atlas. You need only one chart to cover all of R. But a prime that consists of, well, let's be generous. Let's keep this chart. But now we publish a 2-page atlas, and there is another chart, and the other chart could be the interval from -infinity to 0, again with the identity map going to the real numbers. Yeah, that's fine, again with the identity map. This is a different chart. This one only covers half of this. These two charts are compatible because any two charts are compatible. And this is a different atlas, also atlas. Now you say, well, hang on, but you can now, of course, construct an atlas A1000 prime where you take more and more charts into it. For instance, you could take another chart where you take R without the, no, that's not, polar coordinates are not very meaningful here. Well, anyway, you come up with various charts, and you can add more and more charts, and any new chart will be compatible with the old. Well, the maximal atlas will be a maximal atlas once you added all the charts that are compatible. Then it's a maximal atlas. Okay? Because then anyone that's compatible with all that's in there is already in there. Again, this notion of a maximal atlas will become more interesting later on when we lift this restriction, or when we intensify this restriction of the atlas being C0. Okay, now we have all this terminology. The big question is, what is this all about? Well, the answer is, we can look at topological manifolds from 2 points of view. Can look at topological manifolds from 2 points of view. In particular, we can look at objects on these manifolds from 2 points of view. In particular, with respect to objects on the topological manifold. For instance, or example, consider a curve. Consider a curve gamma. What's a curve? Well, let's say a curve is a map from all of R into the topological manifold. Now, you could have the question, is the curve continuous? As it should be if it is the trajectory of a classical particle. So if we identify M with the physical space, we want to do classical mechanics, the particle trajectory shouldn't jump all of a sudden, it should be continuous. You can ask this question on two levels. So answer level 1. Answer level 1 is the following. You say it's a no-brainer because you have R equipped with the standard topology, you have M equipped with the topology you gave it, so it's a topological manifold, and it's full well clear what a continuous curve is. Then you say, well, the curve is continuous if for every open set in the target, the pre-image of that open set under the map gamma is open in the domain. Why? Well, because that is the definition of a continuous map, and the curve is just a particular instance of a map. So you can decide this fully on the topological level. So there is nothing more that needs to be said. Well, however, that is not how so far you looked at it in your physics courses. In the physics courses, you looked at it at level 2, or at least at another level. You said, aha, I have R, I map it into the physical space, all right, that's the curve gamma in the real world if you wish, but now you only look at one part of the real world, namely the image of gamma only into a subset U, so that the domain is the pre-image of U under the map gamma, so that parameter range where the curve lies within this restricted set U. And if U together with X is a chart, then you land in X of U in Rd. Let's say M is a d-dimensional manifold, dim M equals d. Okay. And then you actually were instructed in your physics courses to not look at the curve gamma, but to look at this curve, at the curve X after gamma. And probably you were even instructed to look not at X after gamma, which is a curve from some part of R into Rd. You were instructed to look at the ith component of this curve, because these are, for a given parameter, the coordinates where your curve is. Okay? And then you were instructed to check whether the definition of the curve is continuous in each slot, right? The curve is continuous into Rd if each component function is continuous. Well, this, of course, you can now check, and you check it here. The question is, if you check that this is continuous, do you already, as a map from R to Rd, can you already conclude that the gamma up here is continuous? Well, in topological manifolds, it's very simple, because you know this is the composition of two continuous maps. So this is always continuous. This is continuous if and only if this is continuous. Okay? So it's correct. You can conclude that if the curve is continuous in its components, then the real curve in the real world, not its coordinate representation, not its chart representation, that the curve in the real world is continuous. So if you want a picture for that, you could say the gamma is, so imagine a bird is flying through this room, okay? And then M is this real space, the physical space, if you wish. Well, our model of it, but nevertheless, the real physical space. And the bird does what the bird does. Now, I can decide to look at, to put coordinates into this room like this, x, y, z, something like this, okay? And then I can look at the path of the bird in these arbitrarily chosen coordinates. That's what you're instructed to do in elementary physics classes. You could choose also a different coordinate system. So that would be another map up here. So you choose a different coordinate system. Y that goes into some part of RD, and you consider the bird flight as y after gamma. So that would be, again, the same bird is flying, it's the same trajectory, but you choose to have different coordinate representation. Okay? So this is more like our representation, how we put numbers to the bird's paths. You need to choose coordinate frames. But the real bird fly is encoded in the curve gamma. This is just how we attach numbers to it. And that's why we so often choose coordinate systems. And now it's again a triviality. This is continuous if and only this is continuous. But now, how do we have access to the real bird's curve? Well, we only have access to the descriptions in different charts. And you may wish to consider this map, which is y after x inverse. It's the chart transition map. But the chart transition map ought to be continuous if the charts are C0 compatible. That means if you know that in one chart your description is continuous, you compose it with the chart change, and then of course you could have equally well looked at the bird's path in the other chart, and you know that's continuous as well. So by looking at chart transition maps, you can almost entirely, you can entirely forget about these inner workings, which in some sense is the real world. You can fully forget about what is in the blue part of this. And you can work in some chart, you can change coordinates to another chart, and you describe the situation in full. But it would be a shame, because what you want to describe is here the real world, and you now see why choosing different coordinate systems describes still the same world. Okay? So that's the philosophy behind all of this. And here everything is trivial. You could go either path and you know everything about all the maps. But as soon as we would like to speak about not the continuity of a curve, but say about the differentiability, there is no way we do this via the topological manifold that would maybe present our or model our real world. We then have to impose that these transition functions preserve any of the properties we want to impose on this. So if we impose here that this be differentiable, well, it better be differentiable in another coordinate frame, okay? But then the transition function needs to be differentiable as a map from RD to RD. And then we need to restrict our atlases and so on. So again, in the topological manifold context, this is all redundant, but it will become important later on. And equally well, and that will be on the problem sheet, you can ask when is a map from some topological space M to another topological space N, or from manifold to manifold, when is it, from manifold to manifold, sorry, when is it continuous? You can then choose coordinates for both the domain and the target, and you can extend this picture, and that will be on the problem sheet. So that's the contact of all we did so far to how you describe physics so far, and it's very valuable to understand these relations. See you next time.